Good morning, everyone.
Good morning, sir. So we can start the session, sir.
Yes, please.
Good morning, everyone. Good morning, respected chairpersons, invited guests, teachers, and my dear students. I, Dr. Gauri Nandi from Department of Zoology, Deshbandhu College, welcome you all on behalf of organizers to the 4th session of International Conference on Integrative Chemical Sciences for Health and Environment 2023, organized by Deshbandhu College, University of Delhi. With permission of both the chairs, I wish to open the session. I welcome our first chairperson who will be joining us online today, Professor Raj Kumar Mishra. Let me take this honor to introduce our first chairperson. Dr. Raj Kumar Mishra is currently working as Professor, Department of Chemistry, Institute of Science, Banaras Hindu University, Varanasi, a PhD from BHU after completing MSc from TM Bhagalpur University. He has been teaching experience of more than 17 years in 2 central universities, Mizoram University and BHU. Professor Mishra's research group is currently engaged towards the development of theoretical model for determination of structure, transport, mechanical, thermodynamics, acoustics, and derived associated properties, industrially and scientifically important alloys and amorphous solids during equilibrium and non-equilibrium statistical mechanics. His group has developed the computational codes for their own research program. Recently, he has started MD simulation on protein DNA drug interaction, binding affinities, thermodynamics, and dynamic using amber force field in real environment. Dr. Mishra's experimental group is focused on the study of corrosion inhibition study of plant extracts towards the metal corrosion in different environment using the electrochemical and analytical techniques. He has, to his credit, more than 45 published papers in international and national journals as a star author and also published 2 books in liquid state theory. Sir is reviewer for the important journals like the Journal of Non-Crystalline Solids, Journal of Chemical Physics, Journal of Physics of Condensed Matter, Report on Progress in Physics, Physics and Chemistry of Solids, Metallurgy, Physical Chemistry and Chemical Physics, Material Aerial Transaction, Material Research Express, and the list is long. Some important research publications of Professor Mishra are in peer-reviewed, reputed international journals like the Journal of Molecular Liquid, PCCP, JNCS, Chemical Physics, etc. He has been awarded with prestigious awards including DST Serb Young Scientist Award with the Project 2008, International Travel Support by DST, CSIR, INSA, Chinese Academy of Science Fellowships, and the list is endless. Ranjan Patel, who has completed his PG from IIT Roorkee and PhD from Jamia Millia Islamia University. Sir has more than 17 years of teaching and research experience. Professor Patel's research teaching areas include physical chemistry, spectroscopy, and biophysical techniques. Sir's research specialization includes protein stability, activity in different solvent mediums, and thermodynamics of liquid mixtures. Sir has completed 4 major research projects, and currently another research project is ongoing in his laboratory. Sir has supervised 11 PhD students and more than 55 MPhil and PhD dissertations combined. Sir also has 2 patents to his credit and is a member of prestigious American Chemical Society and Indian Biophysical Society. Sir's list of research publication is long and extensive, and he has more than 130 publications in reputed international journals. Professor Patel has also edited and authored many book chapters and has been invited as a mentor in many national and international symposia and workshops. Sir has organized numerous conferences also and has served on various administrative jobs. I hope, sir, I have not missed any point in the admirable CV of both my chairpersons. I welcome you all, sir. I now request.
Thank you, Dr. Gauri. Hello. Yeah. So good morning, everyone. And good morning, Professor Raj Mishra ji. Namaskar.
Namaste.
Welcome, sir. So I welcome you all in the second day, fourth session of ICHE 2023 conference. And in this session, we have four speakers. So our first speaker is Professor Ram Singh. He is professor in Department of Applied Chemistry, Delhi Technological University. Sir did his bachelor and MSc from Ramjas College, University of Delhi. And sir also performed his PhD from the Department of Chemistry, University of Delhi, under the supervision of Professor SMS Chauhan. And sir is published more than 100 research papers, 16 books, 25 book chapters, and 31 modules of EPG Pathshala. He contributed in more than 19 symposia and seminars. He has 2 patents from his works, and his group currently working in the challenging problems related to human health and society, giving emphasis on neurodegenerative disease like Alzheimer and Parkinson's diseases. So, sir, I welcome you, and kindly please do your talks to answers. Actually, sir, you have 25 minutes for your talk. Thank you so much. Please. Please.
I think I don't need a mic. I'm audible,
Yeah.
right? So, thank you, Chair.
Unable to hear Professor Ram. Please check the audio system.
I think now I'm audible. Professor Mishra, you are mute. Anyway.
Yes, sir. Now I am able to hear you. Thank you, sir.
Thank you.
Thank you.
So, moving slowly. Okay, I will manage. Slow है. Anyway, so slow, I think. The PPT is moving very slowly. Anyway, so if you will go to the dictionary and you find the definition of a dementia, this is a mental process, persistent disorder of the mental process, which is caused by the brain disease or injury and marked by the memory disorders. But sometimes we forget the things in a daily life. This is not the history that we have faced this type of problems. There is an umbrella of diseases associated with the dementia, and about 60 to 20% of the conditions is for the Alzheimer's disease. So, if you will see the when this was discovered in 1906 by Dr. Alzheimer, and he at that time this disease was considered to be a rare disease, but with the time now have a millions of people getting affected by this disease. So a notion in the beginning that only the older people get affected, but as the time passes, even the people with the age group of 40 and above, they are getting affected by this disease. And there are so many pictures available on this disease. Like you can check for the is a picture called Black by Amitabh Bachchan. Then there was recently that Uri. So if you have to define Alzheimer's disease, this is irreversible. Irreversible means even if you are giving the medicine, that will not go back. You have a progressive brain disease that slowly destroys memory, thinking, behavior, language, communication skill. This comes in the stages. You have a first stage, second stage, third stage. In the first stage, this is the initial symptoms of forgetfulness, losing track of the time, getting lost in the familiar place. In second stage, people tend to forget the recent events, people's name. We can find it difficult to communicate. And in the third stage, this is total dependency. When people reach to the third stage, this affects all budget, social, personal relations, everything. According to WHO, this is the 7th. This is the 7th leading cause of death here. I think this will not work on this one LED, the pointer. And if you'll see the gap between the 2000 and 2019, this gap is only here. So there is a possibility that this will go to the first, second, third, fourth positions very soon by 2030 or 2050. By 2050, there is expected that 106 million people will be affected by this disease. If you will compare the male and female, this is the, I think this is going above. This is for the female part. This is for the male. So even at the age of 45 or at the age of 65, the ratio is double. Females are more prone to get affected by the Alzheimer's disease than the male. From the Indian perspective, at present, as per the data available, 40 lakh people are suffering from this disease, and by 2030, it's expected to be 80 lakhs. So we have a 140 crore population average almost. In that, if 80 lakh people are suffering by 2030, that is alarming to take care of that. As per the report of the National Crime Record Bureau, 2016, more than 13,000 people has lost their houses, while they cannot locate it because of they forget the places for where they have to move. And when we're talking about the death on the seventh place, that includes both direct death as well as indirect death. Direct death means you have a disease, with time you succumb to that disease. Indirect means suppose you go from the house, the elderly people go from the house, they forget that they have to return back, they died somewhere. So that data is also collected by few NGOs. So this affect your budget, social, personal, everything. COVID has added the percentage increases in the COVID time. Still, a lot of R&D work is going on. What are the possibilities that why this during the COVID time the things have changed? You'll find so many reports available where they say that Alzheimer's disease has increased in the COVID time. The first lady who developed this disease, and the doctor was Dr. Alzheimer, who treated this disease lady, and she has developed that disease in early 50s only. While giving a lecture, Dr. Alzheimer has given the term Alzheimer's disease for this type of behavior, that the symptoms they are showing that you forget some things. You have a hallucination basically also, that you feel that some person is coming and going to kill you. So there is a story, if you will read by the available in the internet, that how she was disturbing the personal relations of the family. She was working somewhere else in some garden, and she suddenly comes running that someone is going to kill her. That was almost the first stage. Now, what happened exactly is, this is the size of the healthy brain, and this is the size of a Alzheimer brain. So what happened? There is a shrinkage of the brain takes place in the slowly and slowly. Now, when this will shrink, what happened that all the communication is basically because of the neurons present in your brain. So when this will shrink, the nerves will automatically have some impact. Their usual communication pattern will get disturbed. If you compare normal brain, this is the brain of Alzheimer's in advanced stage, and the percentage reduction. You see that 10 to 12% reduction is almost taking place in the brain. So how this causes the problem is this is a simple neuron. And in Alzheimer, what happens? This neuron develops depositions inside as well as outside. So suppose you will take the example that if you have some rubber pipe, suppose neuron is your rubber pipe. Now, if you will put the things outside of the pipe and inside pipe also, the amount of neurotransmitters or the communication that is being carried away by that neurons get decreased. And that's why suppose you are thinking something, or suppose you are responding to something, the response time, thinking time reduce. Now, why this takes place? So neurons work on the three aspects. This communicates with each other, this carry out metabolism and repair itself. Alzheimer's disease disturbs all the three. So neuron cannot communicate with each other properly. So one neuron is giving the information or releasing the neurotransmitter. Second neuron is with the receptor, they are catching the neurotransmitters. So this amount gets reduced. In between the neurons, the gap between the axons, you have enzymes which are hydrolyzing those neurotransmitters, and that hydrolyzing products again go back to for the repair process of the preparation of the neurotransmitters. I will come to that slide. So there are so many approaches for the treatment. These are the possible treatments pathways. This has been discussed. Hypothesis has been discussed. Out of this, there are only 3 drugs. Cholinergic approach is available, approved by the FDA. It also basically cure the symptoms. You cannot go to the complete cure with the disease. So there is a lot of scope to work in this field. There are you will find that within a week, more than 10,000 publications comes on this particular neurodegenerative diseases. So wide open area to work here. This was amyloid aspects, which is hiding in the top. So I will be discussing on 2 only, because that time will permit only for these 2: cholinergic approach and the amyloid approach. In cholinergic approach, basically I am focusing on this part, not on that part. So in amyloid hypothesis, what happened that suppose this is a neuron, and there are certain APP, means amyloid precursor proteins are there. So there are certain enzymes which cut that. So when they cut that, they get deposited. The enzymes you have BACE1, and then you will find that which are available in the literature. So when they cut down, they get deposited, and we have seen that these are the deposition outside the nerves. For the inside, these are the microtubules, which is stabilized by the top protein, which remains inside in this neurons. So inside this get rupture because of the so many factors, and because of the rupturing, these tangles, tau proteins, get deposited inside. So if you will see this one, there is a inside depositions and there is outside deposition. So because of these depositions, these healthy neurons, they get changed either in the shape or in the diameters, whatever the possibilities are there. They are working in the healthy human beings that get affected by that. So this is the one aspect where one can work, that they can work at the point here. First, if you can stop the cutting of that APP, you can develop some inhibitors, which those enzymes which are cutting the APP, if you can develop the inhibitors, they will stop that place, and there will not be formation of these plaques. No drug is available for this part. Same for the rupturing of, you can also stop the rupturing of the microtubules. Again, nothing is available. This takes place because of the background. I will not explain these backgrounds. So these are backgrounds, so many things are going on, and that leads to these type of depositions. You can target any particular places. When you work in the medicinal chemistry field, you find that you can target any particular place. Go to literature, you can find out the molecules responsible for that. You can design the molecules, you can go for the docking studies, synthesize it, go for in vitro. Acetylcholine is a neurotransmitter, and loss of this is responsible for the memory loss. So if you can enhance the cholinergic activity, or you can enhance the formation of acetylcholine neurotransmitters, somehow you are increasing the memory loss, so decreasing the memory loss and helping the people to remember the things fast. You see that in our ancient time, people are using that some herbs like ashwagandha, even curcumin is there in your kitchen. This type of herbs, they are the old literature, some available. They say that somehow that is helpful for the enhancement of the memory. This is what I was explaining, that this is the two neurons. You have a neurotransmitters, acetylcholine, and when it move from here to here, some are get with the receptor when to communicate with each other. Some are hydrolyzed with the acetylcholinesterase enzyme into the choline, and that choline go back again prepare the acetylcholine neurotransmitter, and this process goes on. Now, what happens if a person develops Alzheimer? Obviously, the amount of neurotransmitter coming from this to this will reduce somehow, because there is a depositions. The movement is not so freely available. So already this is coming in less in number. Then this acetylcholinesterase they are hybridizing this one. So again, the number will further decrease. So if we can develop acetylcholinesterase inhibitors or choline inhibitors, then we can stop the hydrolysis here. So the number may increase. And on this principle, people are working for the choline inhibitors. The process of the hydrolysis. So if you will see the fact, there is no cure for this disease till now. This is mainly because the pathophysiology of it is still not fully understood. Beta amyloid hypothesis, we read in the books, but there are always counter publications are there which says that this is possible, this is not possible. Have a combination of cure of the disease. The three donepezil, rivastigmine, and galantamine. These are the acetylcholine inhibitors available in the market, which is being prescribed for the Alzheimer. Even this is also given for the Parkinson's also sometimes. Because in Parkinson's also there is a decrease in the dopamine. That means the coordination of your body parts slowly and slowly not getting controlled by the brain. So it will not give the order that suppose you want to raise this hand, it will not be raised. There is a decrease in the dopamine. So those who are working in the Parkinson's, they can also have a similar working culture with the Alzheimer. And there is another enzyme called MAOB, monoamine oxidase. Their inhibitors is also responsible for the treatment of both the things, Alzheimer as well as Parkinson's. So you find so many literatures are available in the market, the internet, in the book form or journal form in the market. You'll see the structures of these two. One thing is common in all the three is the heterocycles, which is nitrogen content. On this fact, I started reading on these literatures, and we have adopted in our lab is very simple, very traditional. We go to silico, identify the compounds, you can synthesize the compounds, do for the in vitro, then in vivo. Till in vitro, we are doing it and publishing it. Further, we have not achieved that nanomolar range so that we can go further. These are the things that you can do it, clinical trial toxicity. So maximum I have reached to the in vitro stage. When you design a molecule, you can take the conjugates. If you are going to make between the two molecules, there are three possibilities. Either you will have a linker, or you can have a simple CC bond coupling, or you can have a fused molecules. When you are fusing the molecules, your molecular the product will less. If you are just making the CC bond, that almost remains the same. If you are making a linkers with molecules, the molecular weight increases. That goes with the rule of the Lipinski 5 rules, and so other aspects are there that we take care while we are designing the molecules. This is the part what my lab is trying to do, and these are the molecules, very small molecules, heterocyclic molecules there. I am just playing with these three molecules type only, where we are changing the linkers, changing the linkers. One paper I will explain that is under just on 29th. I have defended the hearing in the patent. Other molecules I cannot expose because I am going to file the second one. So you'll see the very small molecules are there that you can link it. The importance of this is always there, that we have identified with the help of in silico study. Other physiochemical parameters are still under investigation. I am also understanding the things. These are another molecules. we are doing in our lab, and we have synthesized more than 100 molecules with having a percentage of 10 to 12% novel molecules. Rest are all of the literature and going for the also comparison with the butylcholine esterase, acetylcholine esterase, how they are affecting the Alzheimer's in vitro positions, not going for the in vivo yet. My research group, this is the current students are working. I'm thankful to my finance, DST, CSIR, DRDO, they are giving me the project. Thank you very much.
Thank you, Professor Ram, for nice talk and about Alzheimer's disease. It's really a great work. And now the forum is for questioner. If any questions, please ask. Please.
Sir, I'm a little confused. I want to know, sir, you said that in the presentation that at one point you want the Alzheimer patients for the treatment of Alzheimer patients, you want to increase the acetylcholine, the amount of the acetylcholine released. But sir, the approach, the acetylcholine esterase inhibitors, if we're using inhibitors against the esterase.
Acetylcholine neurotransmitter you want to increase.
So, okay.
Neurotransmitter you have to increase.
Okay.
Not the enzyme. So if you will inhibit the enzyme, the enzyme will not hydrolyze the neurotransmitter.
Yes, sir.
Right?
Yes, sir.
So the number of acetylcholine coming from one neuron to another neuron will at least will increase if you will stop the hydrolysis portion in between.
Okay. Got it. Thank you.
Maybe slip that you have understood.
No, sir, I have not understood.
Other question? Ram, actually, hope you have already done the toxic effect also. Cytotoxicity.
Not reach that level, still there.
Because it's also
that is the important
issue.
aspect. Toxicity is the very important aspect. We cannot ignore it.
And one thing is that because you have synthesized your molecules already, and so if you have just considered model proteins to check the aggregation properties of these your compounds, maybe denaturation, something.
Maybe.
Or because maybe they just solve the problem of aggregations.
Yeah.
So maybe some experimental approach you can apply.
Thank you.
Okay, sir.
Thank you.
Okay, thank you, Dr. Ram. Thank you so much.
Thank you.
So,
Sir, thank you, sir, for the enlightening session. I now request Professor Patel to please felicitate our invited speaker, Professor Ram Singh, with a token of respect. Now I request Professor Raj sir to please introduce our next speaker, Professor Amitabh Jha.
Okay. So first of all, I'm very much thankful to the organizing committee and Dr. Pratibha especially to give me this opportunity. And I am very happy to introduce Professor Amitabh Jha. Presently, he is professor of Department of Chemistry, University of Avenue Acadia University in Canada. And he has also served in College of Pharmacy and National University of Saskatchewan, Canada. His research area is mainly focused on drug design, synthesis, structure activity relationship, pharmacological study, and kinetic study. And he's mainly focused on the research in discovery of potential drug for the treatment of cancer, bacterial infection, and neurodegenerative diseases. So with these words, I would like to invite Professor Amitabh Jha as our next speaker.
Thank you, Dr. Mishra. Am I audible?
Yeah, you are audible.
Oh, thank you. So thank you, Dr. Mishra, and also thank the organizers for inviting me. I was approached by Dr. Pratibha as well. And this is my second presentation at Deshbandhu College. So I see that the college is doing very fantastic work in organizing the conferences, and as well as letting students, the new students, actually exposed to different types of research. So I'm really happy to see that. I will share my screen now. Is my screen visible?
Not yet, sir.
How about now?
Yeah, now it's okay. Yes,
Okay.
sir. It's okay.
So although one of the major aspects of research in my lab is medicinal chemistry, today actually I'll be talking about synthetic methodology development, especially the green aspect of the type of chemistry that I perform in my laboratory. So as mentioned in my introduction, that I do a lot of work in medicinal chemistry in the drug development process, and the various projects which are undertaken in my lab, they are listed here: selective estrogen receptor modulators, topoisomerase inhibitors, analogs of curcumin, histone deacetylase inhibitors, and we have made compounds belonging to these different types of structures. And also the synthetic chemistry interest that I pursue involves multi-component reactions and that involve a cascade process. And here the several types of reactive intermediates are often seen in my reactions, and these include quinone methides and NS-aluminium ion. And I will be sharing some of my recent results in this area. So here are structure of some of the compounds that we have successfully synthesized using cascade methodology. So green chemistry, actually, these days there are courses being offered in green chemistry, and I think students who take these courses are quite familiar with these 12 principles of green chemistry. In a particular type of research, several of these aspects can be incorporated. And the focus of my research is on prevention of waste, atom economy, use of safer solvents and auxiliaries, design of energy efficiency by using, use of procedures by which you can actually reduce the amount of energy given to a reaction to be performed, use of renewable feedstocks, so certain chemicals that are that basically can be renewed, reduce derivatives, and use catalysis to make your reaction, more efficient. So the multi-component cascade reaction, it is actually pretty simple to understand this. Normally, when a reaction is done, generally, two reactants will be reacted together, a product will be formed, and then it could be a multi-step synthesis, and several steps needs to be done to actually get to a final product. At the same time, it can be envisaged that the various parts of the molecules can be brought together in just one step, and the same synthesis, which otherwise requires several steps, can actually be done in one step. So this cartoon here explains that. And using the multi-component reaction methodologies, certain advantages that actually are quite obvious from that is that it leads to better atom economy, it reduces derivatives, catalysis can be used to improve the yield of the reaction, and you can employ certain procedures by which you can reduce the energy needed for the reaction. There are a number of multi-components reactions which are actually reported in literature, and here are some of them. And I just want to highlight that the type of reaction that I am going to be using in my reactions are the Mannich reaction and Petasis reaction. So the examples that I will give you later in my research projects are going to be mainly involving manic reaction and potassius reaction. Manic reaction is basically reaction of an active methylene with formaldehyde or a non-enolizable aldehyde and an amine to do the aminomethylation on the active methylene. Potassius reaction is basically, it uses an aryl boronic acid in presence of amine and glyoxylic acid, and the product is actually an amino acid. The glyoxylic acid can be changed with some other electrophile, and accordingly the new type of potassius reaction with compounds other than amino acid can also be synthesized. So several years ago, there was one particular project in which I was interested in synthesizing, an extension to a manic reaction. So if you are performing a manic reaction on beta-naphthol using a non-enolizable aldehyde like benzaldehyde and an amine, this is the product that you would expect to get. What I thought is that, okay, if my aldehyde also has an alcohol group attached to it, and if that reaction produces a manic reaction, then the additional OH group can actually be cyclized with the OH group of the phenol to give a cyclic structure. So I thought that how about changing the aldehyde with another aldehyde that also contains a hydroxy group, and that can give rise to a product that looks like this. So for that purpose, I synthesized several hydroxy substituted aldehydes and perform the reaction. So the idea was that first the manic reaction will form, and after the formation of manic reaction, dehydration will result into cyclization and to make a product like this. So this is what was expected. However, when the reaction was done, a different compound was obtained. So if you compare the obtained structure versus the expected structure, it is the amine that is attached at a different position. Also, if you think about the spectroscopic identification of these compounds, since the two compounds are very similar in structure, it is, you cannot unambiguously say whether it is the expected structure or the obtained structure. So we actually ended up doing X-ray crystallography to confirm that the compound we got is not what we expected. However, the product obtained was the different product here. So here is an example of a molecule that we synthesized, which we confirmed the structure with X-ray crystallography. So the interesting part, if you compare the structure, one of the very interesting thing is that the way this product is forming, how would you justify the formation of this product? So in here, we also obtained a minor product in which a simple manic base was also formed, and this was formed to about 10% yield. So this formation of this byproduct was the one that actually helped us to identify how this product was actually forming. So let us pay attention to the byproduct. In the byproduct, we have beta-naphthol, we have the amine, and then we have one carbon, a CH2, okay? And looking at the starting material, we do not see any source of one carbon. We have a aldehyde with a hydroxy group, but there is no source for one carbon. So this was initially surprising to us, but after we thought seriously about it, we actually understood that actually the hydroxyaldehyde that we are using is actually breaking down in the reaction. So with the starting material that is shown here, the main products that were formed, was the unexpected product, and there were two side products. And from the two side products, we can clearly see that there is one carbon that's somehow coming, in the reaction. So how is this one carbon forming? So we basically thought, okay, let's say that, the mechanism is that rather than manic reaction happening, the aldehyde is actually reacting with amine to form the aminal, and then somehow the cyclization is happening on the naphthol, and that's how the product is forming. Now, this cannot be justified because if you look at the position of the hydroxy group, in cases like this, if the reaction follows electrophilic aromatic substitution, then there would be rearrangement because otherwise it is going to form a primary carbocation, but the primary carbocation, since that's not stable, the rearrangement should happen. So this was not the mechanism by which these products were forming. So side products actually helped us identify how this reaction is happening. So looking at the ways by which these side products can be formed, you can make the side products by reacting naphthol and amine in presence of formaldehyde. And formaldehyde can actually form either of these side products. And we were very sure that we did not use formaldehyde in our reaction. So basically, somehow formaldehyde was forming after breaking down of the aldehyde that we used. So basically, our aldehyde, we propose that our aldehyde is actually breaking down into formaldehyde and isobutyraldehyde through a retroaldol condensation. And after we got this idea, explaining the whole synthesis was easy. So basically, the retroaldol condensation is actually making the formaldehyde and isobutyraldehyde. Then formaldehyde is reacting with amine and naphthol to make a simple manic base, and this manic base is deaminating to form a reactive intermediate called quinone methide. So quinone methide is this structure right here, and then this isobutyraldehyde, which is forming, actually goes on to react with the liberated amine to form an anamine, and this anamine reacts with quinone methide through a inverse electron demand Diels-Alder reaction to cyclize and give the product. So this is what we proposed, and this was basically fitting very well with our observation. However, we wanted to confirm that actually this is the mechanism. So to confirm this mechanism, we actually perform additional steps. So we've synthesized this manic base, which was obtained as a side product, and with that compound, we reacted isobutyraldehyde, and this also led to the formation of product. So clearly, manic base was one of the intermediate in the reaction, and then that deaminates, and the liberated amine reacts with the aldehyde, isobutyraldehyde, to form the anamine, and the Diels-Alder cyclization happens to give the product. So when this happened, when we did this reaction, I was first introduced to quinone methide. I was not familiar with the quinone methide intermediate at that time. And I found the structure of quinone methide to be very interesting and the type of reaction it gives. So I started exploring this chemistry more and more. And based on that, we have actually done a number of reactions so far. We have published a number of papers, but today I'm going to be sharing with you some of the quinone methide chemistry that we have recently performed, and we are about to publish those reactions. Later on, rather than making the hydroxyaldehyde, which actually breaks down by retroaldol, we thought, why actually make this compound? Why not just simply use naphthol, amine, isobutyraldehyde, and formaldehyde as a one-component reaction to produce the product? And in fact, when we tried this, we did get the product. So we developed a 4-component reaction to make these naphthopyran-based compounds. So, we were very happy to obtain these results. Now, after we made these compounds, we thought, okay, the product, this naphthopyran on which there is amine substituted at position number 2, we thought that this compound actually can be hydrolyzed and the nitrogen can be replaced with an OH group. So, because it's essentially an aminal, and aminals can be hydrolyzed. And we came across another molecule which is called splitomycin. And if you look at structure of splitomycin, it's a very simple compound. It's a lactone on naphthol. Okay, so I was able to notice that the kind of compound we are making, we can actually convert them into splitomycin analogs. So what we did is we first hydrolyzed our compound to get the hydroxy substrate product. Now this can be called a lactol, and this lactol compound can then be oxidized to the corresponding lactone. And in this one, we can have three substituents, R on benzene ring and R1 and R2 on the side chain of the, as a side chain of the pyran ring or the lactone ring. And if you compare this structure with splitomycin, these are clearly analogs of splitomycin. And splitomycin is actually a reference compound sold in, Aldrich catalog as a selective histone deacetylase inhibitor reference sample. So we made a series of these compounds by following this condition. So hydrolysis of the aminal produces the lactol, and we were able to oxidize the lactol into lactone using the Jones reagents. Now, Jones reagent is, although it works very well, but it is not a very, it's quite harsh conditions, and chromium is a toxic metal. So we then decided that can we actually do the oxidation using some easier conditions. So in developing easier conditions for that, we were actually able to make the lactol in one step by adding ethanol and water into the reaction medium. So when we use just simply the the PTSA and microwave in solvent-free condition, we get the aminal. But when we use ethanol water in the reaction, we actually get the lactol as a product. So we have to do one less step to get to the lactol. We don't have to additionally do the hydrolysis. And then the oxidation that produces splitomycin analogs, as I said, we were able to develop procedures using IBX, as an oxidizing agent to convert lactol into lactone using with a very good yield. Now, the overall yield of our product, we made 14 examples, and our yield were actually in the range of 36 to 70%. And the mechanism, as I explained to you, basically first, the naphthol reacts with formaldehyde and amine to make the manic base. Manic base then deaminates to release the amine and turns into a quinone methide. The amine then reacts with aldehyde to produce an enamine, and then the Diels-Alder reaction happens to give the product, and then hydrolysis of the product produces the lactol, and oxidation of lactol gives the lactone. So basically, in two-step process, we are able to do these 6 steps. So from manic reaction all the way to hydrolysis, these 5 steps were actually done in one reaction part, and finally the oxidation step was done separately. And we were able to get this compound. So if you were to look at the yield, a 36% of overall yield in a 6-step reaction means an average yield of 84% per step. And for our best yield, which is 69%, the overall yield for a 6-step reaction means an average yield of 94%. So what I'm trying to highlight here is that, when you are doing a cascade process, and if you are not doing so many steps one after another, then your yield is going to be much higher, which is demonstrated here that, a 70% yield looks like that we are getting almost 90% conversion for each of these 6-step process. Now, one of the projects that we have just finished recently, it also uses a quinone methide condition, and we actually developed a 4-component reaction to make this. So in this one, we know that use of manic base produces the quinone methide, and quinone methide then does interesting cyclization reactions. But we have realized that we do not have to make manic bases. We can actually use the components of manic base and react it with the other reagent to do the cyclization. So in here, we actually used naphthol, formaldehyde, amine, and this alkene here. Now, if you pay attention to the structure of this alkene, on one side of the alkene, there are 2 electron withdrawing ester groups, and on the other side, it's a vinyl ether, and vinyl ether makes the alkene double bond electron rich, whereas the ester make it electron poor. So these types of alkenes are called push-pull alkenes. Push-pull alkenes meaning that the electron is being pushed by one type of group and electron is being released by another, so there is pulling and pushing of electrons simultaneously. So in this, we wanted to see whether the Diels-Alder cyclization takes place with the quinone methide or not. And we were actually very pleased to see that the cyclization was not only happening, we were also getting a product which was unexpected. So if you look at the diene structure, this push-pull amine, it contains an ether group, whereas the major product actually, in place of the ether group, it contains amine, and this amine is the deaminated amine which gets utilized in this reaction. So basically, we made 15 analogs and the yields varied from 20 to 46%. And the mechanism, very similar to what I have proposed earlier, that first the mannich base is formed, mannich base then deaminates to form a quinone methide, and quinone methide basically then reacts with the alkene as the dienophile. Now, this alkene dienophile can either be this vinyl ether alkene, or this vinyl ether alkene can react with amine to make a, the anamine type alkene. So either anamine type alkene or the vinyl ether alkene, both of those can react and they can produce, the major product contains the amine, whereas a minor product contains the ether linkage there. So in our process, we saw that again, mannich base was deaminating to make quinone methide. Now, quinone methide is a reactive intermediate. It does not have a long half-life, long shelf life. So basically, it is formed in the reaction and that gets used with either a nucleophile or with some kind of a dienophile present in the reaction. Another, so basically in here also there are 4 steps happening: mannich reaction, deamination, anamine formation, and finally the hetero-Diels-Alder reaction to give the major product. Another project that we did here was basically, another electrocyclic reaction, but for the starting material of the electrocyclic reaction, we wanted to make some cyclic tertiary enamides. And for that, we used 2-acetyl benzoic acid, which is a keto acid, and this was reacted with aniline, and the idea was to make an amide bond. However, after the workup of this reaction, we obtained this product, and I'm calling this product cyclic tertiary enamides. Tertiary enamide because if you look at this highlighted side, you have an amide, and that amide is in conjugation with an alkene. Such groups are called enamides. So this is an enamide, and when I looked at the synthesis of these compounds, I found that previously other people have made the same compound using rhodium catalyzed condition on Schiff bases using carbon monoxide. So our procedure is experimentally quite simple to get the same compound. So we made about 20 analogs of this tertiary enamides. And then, so basically, as I said, the initial idea was to make the amide. So the peptide coupling reagent EDC in presence of DCM forms an amide bond. We were expecting the amide bond to form, but what we also noticed is that the amide did an intramolecular cyclization to make this hydroxy product, and that got dehydrated to produce the tertiary enamide. So we had these 3 steps happen in the same reaction part. And then finally, we use this tertiary enamides and we reacted them with quinone methydes to do an electrocyclization. And to our amusement, we were actually able to obtain such products. So this time we reacted manic bases with cyclic tertiary enamide in microwave reactor, and the corresponding cyclized products were obtained. So what happened here is that the deamination happened, and the manic base got transformed into quinone methide, and this quinone methide did electrocyclization with the double bond of the tertiary enamide to produce this product. Now, if you look at the complexity of this product here, we have a naphthopyrin ring, we have an isoindolene ring, and there is a spiral linkage between the two. And there is one chiral center in the molecule. So in this microwave reaction, there were two steps happening: deamination of the quinone methide and the heterodyl-Solder reaction to give the cyclization. So we are again finished this project, and we have obtained most of the data, and we are in the process of writing manuscript on this one. Now, I told you that I'm also working on NSI aluminium ion in my lab. So there is some work that we noticed which we thought we can improve on. So reaction of an alkyne carboxylic acid with dinucleophile in presence of a gold catalyst forms a tricyclic product, as you can see here. We found this paper, and then in this paper there are a couple of problems. The problem number one is that the alkynoic acid is actually a very expensive reagent. 1 gram is about over $100 for the alkynoic acid. And also the catalyst is gold catalyst, and gold itself is again another expensive material. So we thought we can actually make this compound relatively cheaply. So what we did is we actually replaced the alkynoic acid with levulinic acid. This keto acid, the first keto acid shown here, that's levulinic acid, and this can be obtained from sugar. So it is actually quite cheap and biorenewable. We made a mixed anhydride of this levulinic acid and reacted that with this molecule containing 2 nucleophile, the amino as well as hydroxy, and then at room temperature reacting with the mixed anhydride, we were able to obtain the same cyclic product. So if you look at the reported literature versus what
Sorry to interrupt you. Can you please hurry, because another speaker is waiting for his turn? Please.
Sure, I will
Thank
finish
Thank you.
in a few minutes. So this cyclization proceeded quite well, and we were able to obtain in one step as well as in two step a pretty good yield of the product. So mechanism is described here. Basically, the electrophile get attacked by amine first, and then the internal cyclization, formation of NS aluminium ion, and the NS aluminium ion gets attacked by the hydroxy to produce the cyclic, tricyclic product. Now, based on this particular reaction, we actually made heterosteroidal compounds. So, if you compare the structure of this NO heterosteroid with estradiol, you will notice that the tetracyclic ring is very similar to what is found in heterosteroids. So we synthesize these molecules using the chemistry I described in the previous slide, starting from aminonaphthalene, use of RCN in presence of two different types of Lewis acid. We were able to do the acylation at position 1, then simple reduction, and then use of keto acid to cyclize. We were actually able to make the NO heterosteroids, and the mechanism is pretty similar to what I have highlighted in the previous slide. Another paper in which we again made another type of heterosteroid. In this paper, we used the alkynoic acid, and that was reacted with, again, naphthylamine, and use of gold catalyst, we were able to actually make this azasteroid. And the same compound after like just that, this was done in 2015, but we have now used, in place of alkynoic acid, levulinic acid to make the same set of compound using much cheaper and much easier chemistry. Now, just one last project that we are using. I told you in the beginning that the petasis reaction is being used in our reaction, and we are in our lab, and we are modifying petasis reaction to make new types of chemistry. So this time we are using petasis reaction to make xanthines. So basically, you know, the petasis reaction is described here. There are different types of petasis reaction. What we have done is we have replaced, we are using boronic acid, we are using the salicylaldehyde, which is also used in petasis reaction, but in place of the amine nucleophile, we are using a phenol. And our idea was that we can perform the petasis reaction, and we can eventually do a double dehydration reaction to produce, xanthines. And when we performed this reaction, we actually got, interesting results. First, in the first result, the expected product with the boronic acid phenyl at the bridge, that is what was expected, but it was not formed. An unexpected product was formed, which was also a xanthine, but it was unsubstituted at the bridging position. So that was one project. And then in a modified attempt, when we used copper triflate in the reaction, we were actually able to install the phenyl ring from the boronic acid at the bridged position. So we were able to make both types of xanthine using the modified petasis protocol. And in interest of time, I'm going to skip the mechanism that we have proposed for it. So in conclusion, we have used the multi-component reaction to make different types of complex structures, and most of these chemistry that I have discussed with you, they involve reactive intermediates such as quinone methides, NS aluminium ion, and carbocations. And finally, I would like to thank my group who have contributed in making these compounds. And finally, I would like to thank you for your attention. Thank you.
Okay, thank you, Professor Jha, for your intensive and extensive and innovative research presenting here. And now session is open for a couple of questions. If someone has any. Yeah. And I have one question that how do you manage the kinetic when you do this pushing and pulling of electrons simultaneously? That reaction will be very fast, I think. And because your area is also pharmacokinetic study, so what kind of work do for that?
So when you talk about the alkene that has both pushing and pulling, generally speaking, when you do an inverse electron demand Diels-Alder reaction, the diene part is electron poor and the dienophile is electron rich. So whenever we use an electron rich dienophile like vinyl ether or enamine or enamide, reaction works very well. But in case of the push-pull alkene, the electron withdrawing group should actually slow down the reaction. So we did that reaction to figure out how much of electron withdrawing effect will actually stop the reaction, and under what condition the reaction will go. And we were surprised. We were actually not expecting the reaction to work because there was two ester groups withdrawing electron, but still the reaction went. So we are interested in actually doing some molecular modeling to understand some DFT calculations to understand, what is an actual requirement, electronic requirement for such kind of cyclization.
Okay, thank you. Yeah. If you have no question, then we should thank to Professor Jha with a clap. So now the next speaker, I think sir will introduce.
Thank you, sir. Yes, sir. Thank you, Professor Jha sir for enlightening lecture. I request our IT team to facilitate with Dr. Jha sir with a token of respect.
So, Professor Jha, do you do any molecular MD simulation also? Oh,
Say
thanks.
that again.
MD simulation, any MD simulation for this drug design or drug synthesis, this modeling? No.
Yes, we have some collaboration where I am able to use expertise for molecular modeling lab in Toronto. So I take their,
Okay.
and I thank you for this wonderful memento.
Thank you, sir. Thank you, sir, for enlightening us. Thank you.
Thank you.
I now request Professor Patel, sir, to please introduce our next speaker. Dr. Siddharth Sharma.
Our next speaker is Dr. Siddharth Sharma. Dr. Siddharth is currently working as an assistant professor in Mohanlal Sukhadia University. He did his postdoc from Pohang University of Science and Technology, South Korea. He was the DST inspired faculty in Guru Nanak Dev University, Amritsar. Dr. Siddharth is working in the research area of electro-organic synthesis post-UGI cyclization reaction and has more than 45 publications in renowned journals. He is availing many research grants from various agencies like UGC, SERB, DST. So I welcome Dr. Siddharth. Now, please, time starts. So I hope you finish your talk within given time. Thank you. Please.
Professor Pratibha and organizing team for organizing such a nice event and giving me opportunity to present our work, what currently we are doing at Mohanlal Sukhadia University, Udaipur. So in next 20 to 25 minutes, I would be talking about the current work we are pursuing at Udaipur, that is from flask to electrochemical cells, and our progress in studying the organic chemistry of isocyanates. Largely, our group is working in a sustainable organic synthesis where we are trying to develop new methodology as well as synthesizing some novel heterocyclic molecules that are embedded and biologically pre-validated. These are major research area currently we are pursuing. First one is isocyanate in multi-component reactions, where we are trying to synthesize some precursor using the multi-component reactions, and these multi-component reaction can be cyclized via different reagents and the catalyst under different conditions. Whereas recent renaissance in electro-organic synthesis forced us to merge our small expertise we generated in the isocyanates chemistry with the electro-organic synthesis, and recently we have also completed few projects over there. More recently, we have also started working on sp2ch bond functionalization utilizing organic electro synthesis, where mostly we are concentrating on the indazole based chemistry. So when I have joined my independent career, one of the functionality which I became interested very recently since the 2018 is the isocyanates. These isocyanates are historically very old molecule, and the first isocyanate was synthesized in 1859 by Leakey by the reaction of allyl iodide and silver cyanides. Whereas these isocyanates generally are stable divalent carbon nucleophile, and one of the peculiar aspects among other functional groups with the isocyanate is that electrophiles and nucleophiles both can attach onto the single carbon atom. Therefore, it has been used as a C1 synthon in organic chemistry. Whereas number of the marine natural products also have an isocyanate as one of the main and core functional group attached to that. So basically, in last 30 to 40 years, this isocyanate chemistry was well accepted by the organic chemists in terms of the multi-component reaction. And here I would like to brief you about the two major multi-component reactions that has been explored and exhaustively utilized by the organic chemists in last few years. Specifically, I would be concentrating on the UGI reaction. UGI reaction is a 4-component reaction where the aldehyde, amine, isocyanate, and carboxylic acid react together to synthesize bis amides. Whereas the Passirani reaction is a milder version and 3-component variation where the aldehyde, isocyanide, and carboxylic acid react together to synthesize alpha-acyloxyamide. Apart from this isocyanide have also been utilized in number of the multi-component reactions such as Grabov backburn, which generates the imidazolopyridine, whereas the amidines can also be synthesized. Generally, these multi-component reaction, what they do is they generate the precursor with a high diversity points, and these diversity points have a multiple advantages specifically in terms of the diversity-oriented synthesis. In early 2000, the Schreiber group at Harvard and David Spring group at Cambridge developed a concept that is called the diversity-oriented synthesis. Basically, this is one way to do the organic synthesis where we can synthesize number of the skeletal diverse molecule utilizing the similar kind of precursors. Majorly, there are two approaches to do these kind of a diversity-oriented synthesis. First is a reagent-based approach, where you have to design your precursor in such a manner that the different reagent would lead to the different skeletal diverse molecules. And another approach, which is generally called as a substrate-based approach and little bit more uncommon, is in which the substrates can be synthesized in such a manner that common condition would give a different mode of cyclization to give the different skeletal diverse molecule. Whereas by taking the hypothesis from this diversity-oriented synthesis, isocyanide-based multi-component reaction, we also hypothesize whether we can also design a precursor in such a manner that the different catalyst and reagent would lead to the different heterocyclic molecule. What we did is we did a small manipulation into the core structure and introduced the hydroxy group. And when we subjected this hydroxy group to the cationic palladium catalyzed 7 endocyclization, we found out that the benzoxazepinones can be synthesized under relatively mild condition. Whereas the same molecule, when subjected to the Escher and Gold catalyst, the 6 exocyclization would lead to the benzoxazine synthesis under very highly diverse condition. Same molecule in which if we can make this amine electron rich, we can also do the hydroalylation reaction via the cationic PD catalyst to generate the 2 quinolone systems, and these 2 quinolones can also be further converted into the different molecule, and we got published this work also. Okay, yeah. So overall, recently we have completed another project where we can also did the spirocyclization using under the electrochemical condition, and the sulfur, selenium, and carbonylation based pyrrolidinone based spirocyclic can also be synthesized. Same molecule can also generate the N-centered mediated radical addition to generate the spirocyclic 4-imidazolidinones. And these molecules can also be further complexified under diastereoselective condition to synthesize tricyclic fused molecules. Whereas recently, the same molecule, what we did is we did the iodocyclization strategy to synthesize the phenanthridine fused heterocycle. So overall, we have developed a concept in that respect that the same molecule would undergo a different mode of cyclization to synthesize a number of the different cyclizations and synthesize very important biological heterocycles. Specifically, I would be concentrating in the first part on this work where we did the cascade kind of cyclization. Our inspiration in this work comes from the 3 classical work which has been reported earlier. First one developed by the Srivastava group. What they did is they have taken they have synthesized the Ugi precursor, and this electron-rich amine would further undergo the acid-free post-Ugi cyclization for the complex tricyclic skeleton. Whereas the He group and the Eric group at the Belgium, they have also introduced a hydroxy group at the aldehyde or the amine group at the hydroxy group at the amine. What they did is they also did the gold catalyzed spirocyclization to synthesize these complex molecules. One of the major drawbacks associated with these cyclization previously reported is they always require a prerequisite of the electronic activating group. We thought if we could able to remove this activating group and did the similar kind of cyclization, that would definitely enhance our procedure. What we have done is we have removed the activating group from the amine, and under the iodinium-based spirocyclization reaction, we could able to synthesize the phenanthridine-fused heterocyclic ring system. And this methodology was definitely much better in terms of many aspects. This was the metal-free approach, whereas in all the cases, the distereoselectivity found greater than 20:1, and the number of multiple CC, CN, and CO, as well as the CI bond formation took place into the reaction, and total 27 compounds were synthesized. Some of them I am showing here, where in all the cases we could able to diversify specifically in terms of the alkynoic acid, as well as the amine has also been varied, and number of the different isocyanide has also been varied, and in most cases the diastereoselectivity was excellent. So total 27 compounds were synthesized, and yield were ranging from the 52 to 87% yield under the cascade synthesis. We did not stop ourselves to generate the 4-point diversity. Since the alkenic iodide were present into the reaction, we further complexified and diversified our molecule by doing the Suzuki cross-coupling reaction to generate the 5-point diversity into these molecules to synthesize the Suzuki coupling product in the 63% yield, whereas the Sonogashira cross-coupling reaction also generated the alkynic system and gave this our product into the 72% yield. This is the proposed mechanism of these molecules, where this iodinium ion, which have a low sigma star orbital, that can be easily interact with the alkynic system to generate this intermediate, and this intermediate undergoes the ipsocyclization followed by the Friedel-Crafts of the cyclization under the to synthesize this phenanthridine-fused heterocycle. The diastereoselectivity was indeed carried out by the single crystal analysis. Since previously these kind of polycyclic heterocycles were reported for their anti-cancer activity, even though we are not medicinal chemists, but we found out that this is always better to try these molecules under check for some biological activity. We did some collaboration and found out that few of the compound have active against the MCF7 breast cancer cell line at the 2.41 micromolar concentration. But when we compared with the doxorubicin, we found that these are not that potent enough to pursue further, but at least we have shown some glimpse that these kind of molecules also have a potential for further medicinal chemistry research. This is the second project currently we are pursuing in our laboratory, that is organic electrochemistry. It will go into the definition of the organic electrochemistry. This is a branch of organic synthesis where molecule can be oxidized and reduced at the anodes and cathode respectively to synthesize some intermediate, and these intermediate would definitely give the some different kind of rearrangement and reaction to synthesize some novel molecules. There are two approaches which are generally considered for doing the electroorganic synthesis. First one is a direct approach, where the substrate directly come into the contact with the electrodes and give the heterogeneous electron transfer. And these heterogeneous electron transfer can be placed in terms of anodic oxidation or the cathodic reduction and gives the intermediates. And these intermediates would give the follow-up reactions to synthesize product. But one of the drawbacks associated with this direct approach is the reaction or electron transfer takes place between the electrode and substrate is heterogeneous in nature, so sometimes yield would be drastically reduced in many aspects. But indirect approach, that is more correlated with the photoredox catalysis, where this mediator transfer its electron with the electrode to generate the mediator takes electron or give up electrons to generate the active form, and this mediator will transfer electron to the substrate under the homogeneous electron transfer to give the reactive intermediate, and finally follow-up reaction give you the products. So chemists, according to their needs, have utilized these direct approach and indirect approach to synthesize some novel chemistry. This is one of the prime case study which I would like to explain in brief, which shows the power of the electroorganic synthesis. This water group in 1982, what they did is they could able to reduce ethyl alcohol under the traditional Birch reaction condition, where the sodium and liquid ammonia at minus 78 degrees centigrade could able to reduce these molecules. But Baran group in 2019 published a seminal paper in Science, and what they did is they could able to achieve the same reactivity under the non-cryogenic condition at the room temperature, as well as the very cheap electrodes were used for doing the electron transfer, and they could able to show this product at the multi-kilogram scale, which indeed show the power and utility of the electroorganic synthesis. Therefore, the academia and industry happily took over these concepts. Our inspiration in this area comes from the basic concepts of the electroorganic synthesis, as well as the reactivity of the isocyanate, which is already available in the literature and what we have learned in last 4 to 5 years. Basically, any organic molecule which have a low oxidation potential can be oxidized to convert into the radical cations, and these radical cations can somewhat cleave to generate the radicals, and this radical can be directly associated with the isocyanate, and which is a well-known methodology in the organic synthesis. Whereas these radicals sometimes are not that stable enough and further can be oxidized at the anode again to generate the cations. But these isocyanide have a nucleophilic center at the carbon, can also react with the carbocations. Whereas some of the organic molecules which have a low reduction potential can undergoes the cathodic reduction to generate the radical anions, and these radical anions can generate the anions, and these anions can directly react with the carbon center, which is electrophilic in nature. So overall, that is the reason that these isocyanate are generally considered as a stereoelectronic chameleons, where according to the needs, they change their reactivity. But the first molecule which we became interested is carbodiamides. These are well-known peptide coupling agent in terms of the EDC and DCC. And when we scratch out the literature, we found out there is no efficient method was available for the synthesis of these carbodiamides. And when we further goes deep into the literature, we found that there are two methods which are available for the direct coupling of the amine and isocyanate, where in the first work, which was published in 2015, this amine isocyanate directly can be coupled in very exhaustive oxidative condition in presence of iodine to synthesize these carbodiamides, whereas this amine can also be converted into the azide to react with the relatively mild condition, but palladium as a catalyst to synthesize this carbodiamide. We also knew from our from the literature that these isocyanides have a very high affinity towards the electrophile, specifically with the iodine, and easily it can generate the diiodoimines. And these diiodoimines, we hypothesize whether if we can couple this diiodoimine, which was generated electrochemically to with the amine, we could also synthesize these carbodiamides. What we did is, after a lot of optimization studies, we found out that this amine and isocyanate can be directly coupled with the PT-PT electrode, and tertiary-butyl ammonium iodide was used as an iodine source as well as the electrolysis, and the acetonitrile was used as a solvent, and the 50 degrees centigrade would be required to do the reaction. After doing the optimization condition, the different substrate scope were realized. The amines which have an ortho meta para substitution and electron donating, electron withdrawing, di-substituted amine have also been realized, and in most of the cases we are getting the moderate to better yields. In case of the cyclohexyl isocyanate, apart from the cyclohexyl and tertiary butyl, we have also utilized the aromatic isocyanate. One of the interesting example I would like to show, and you would appreciate more, that we could also able to synthesize this DCC, which is a well-known peptide coupling agent, but could able to synthesize these molecule in only 26% yield. But after publishing paper, one of the pharmaceutical company got interested in this molecule, and currently we are trying to pursue that how we can increase the yield so that it is more industrially viable. So these are carbodiamides are well-known intermediates. We could able to hydrolyze these molecules under acidic condition to synthesize the corresponding differentially substituted urea. if you see the mechanism, after a lot of cyclic voltammetry studies, as well as on control experiment, we found out that the tertiary-butyl ammonium iodide, which have a low oxidation potential, and this iodide at the 0.7 volt itself can be converted into the iodide radical, or maybe via the pathway 1, where the iodine can also be synthesized, can directly react together to generate the intermediate A, which is a diiodoimines, and which gives the alkenic nucleophilic substitution reaction to synthesize carbodiamides. And these carbodiamides can be overall synthesized after the complete the reduction cycle, where this H plus give us the hydrogen as the sole and only byproduct within the reaction. So after completing 1 or 2 projects of methodology development, we thought whether we can also synthesize some novel molecules using the electroorganic synthesis. Since we had a small expertise generated in the post-Ugi cyclization, what we did is we electrolyzed these Ugi reaction products under the electrochemical condition, and we could able to synthesize this 4-imidazolidinone spirocyclic ring system. These molecules are well-known insecticidal and available into the literature in the form of hetacillin, spiroxatrine, and spiropyrinones, whereas this Macmillan organocatalysts also have a similar skeleton, which is much similar to what we synthesized. After a lot of optimization studies, we found out that the different solvent can all used in specifically the hexafluoroisopropanol, methanol, and trifluoroethanol were used, and different mixture of organic solvents were also used. In the case of the electrolytes, the tetrabutyl ammonium tetrafluoroborate, LiClO4, and NPF6 electrolytes were also used, and different electrodes also have been utilized for doing the reaction. But what comes out after almost 150 the optimization reaction, that without hexafluoroisopropanol reaction was not going out, and the electricity was indispensable for the reaction, and since the electrolytes was also very necessity for moving the reaction forward. So overall, we got the optimized condition where revitrified carbon anode was used, as well as the PT was used as a cathode, and hexafluoroisopropanol was used as a solvent, and electrolytes and 8 milliampere current gave the model reaction into the 74% yield. In this case, the number of different carboxylic acid scope have been realized, where the ortho-meta para substituted, tri-substituted, pentafluoro substituted, as well as the long chain aliphatic acids have also been used. Different scope of aldehyde also been realized, where this was confirmed by the single crystal analysis. Scope of ketone were also used where we did the Ugi reaction from the cyclopentanone to give this the distinct skeleton of the tri-spirocyclic molecules. One of the drawbacks associated with this reaction, that in most of the cases when the electron-rich amine were used, then only the reaction was going forward. And even when we used the paramethylamine, then even then we were not getting any product, and all the products that the methoxy group was one kind of a precondition for doing the reaction. This is the scope of labile group, where we have used a different labile group which are electrochemically labile in one aspect, that generally degrades, and we could able to show these products under, especially in the boronic acid case, we got the 63% yield, and the secondary alcohol containing lithocholic acid also did the latest state functionalization for the spirocyclic 4-imidazolidinones. So before going into the proposed mechanism, we did some control experiment. We found out that when we did the CV study, we found out that the 2 peaks at 1.1 volt and 0.7 volt, but at that time we did not know that which specific peak belongs to which fragmentation of Ugi product. What we did is we did some knockoff studies where we synthesized another molecule, that is 7A, in which one of the methoxy group we removed and synthesized the molecule. We found out that the peak, which is 1.1, was converting into the 1.3, whereas at the same time, when we did the interchange of the methoxy group and synthesized the compound 8A, what we found out that the peak which was we were getting at 0.7 volt, we were getting at 1.3 volt. So after combination of all these three, we found out that the 0.7 volt belonged to this group, which is coming from the isocyanide, and the amidic group was oxidizing at 1.1 volt. And in generally, the electroorganic synthesis, the lower oxidation potential have a high tendency to oxidize first. since the reaction was not going into the hexafluoro,
Please,
Yeah.
wait for, because
yeah,
already late now. Thank you.
this is the
Beautiful.
last slide actually. So we also did some titration studies in which since HFIP was playing an efficient role, we did some titration study. We mixed HFIP with the solvent and the compound, and we found out that this amidic NH was going the low delta value. It means that the HFIP was directly correlating and making this NH electron rich, which is making it prone to be oxidizingly favorably. We also proposed the intermediate, and we tried to recrystallize this molecule with the HFIP, but we did not succeed there. So this is the proposed mechanism. So preferentially, this molecule was oxidized as a radical cation. This hexafluoroisopropanol have a low cathodic potential, can be converted into the oxides. It can abstract a proton to generate the intermediate B, which have an N-centered radical, which give the ipsocyclization reaction to anodic oxidation to synthesize our desired product. So apart from these, we are also doing some indazole functionalization and multi-component reaction using the electrochemical synthesis. This is the recent paper we published in OrgLat, where we could do the different molecule synthesis on the modulation, the cell voltage of the reaction. What we did is we did the acyl oscillation at the 3.5 volt and got the acyl oxylated product. When as soon as we increased the voltage from the 3.5 volt to the 4.7 volt, we did from the C3 acylation to the N1 acylation of the product. So we could able to show the structural dichotomy based on to the cell voltage of the reaction. This is the novel multi-component reaction we have recently reported that under the electrochemical condition. So I am lucky to be working at my native place, that is Udaipur, and we are very proud of a lot of things, especially Maharana Pratap. He is sitting high hill of the Udaipur at the world tallest bronze statue. This is the famous Lake Palace Hotel. And this is the Fateh Sagar, where you can, at the evening, you can roam around and enjoy the beautiful evening. This is our laboratory, what we are doing currently. And we also have, recently, we also 2 years back bought rotaviper, and especially thank to my students who are without having the rotaviper facility on distillation assembly, they are doing this organic synthesis we performed in last 4 to 5 years. This is previously I was lucky to have fundings from the in terms of Inspire faculty, and recently completed one project of SRG grant. These are the 2 students. The first one, the post-Tugi cyclization work was did by the Dr. Karandeep Singh. He is currently working at the pharmaceutical industry, and the electrochemistry work was started by Bhavar Kumar Malviya in 2018, and currently he is a regular scientist at the Graz, Austria. These are the 2 students currently working and further pursuing our work. Thank you.
Good, Dr. Siddharth. So we have very couple of questions, if anybody have.
May I ask one question? Dr. Siddharth, you are doing this electrochemical organic synthesis. So the final product you are getting on electrode or in solution system, electrolyte system? Am I audible? Am I audible?
So audible, please.
Yeah. So, Dr. Siddharth.
Now I'm audible?
You are.
Yeah.
audible.
Yeah, I heard your question. The thing is, that generally these electron transfer takes place at the anode or cathode, respectively. But generally, we are getting the products at the solution state only. So until and unless you use some metal catalyst in the electrolysis, then there is a chance that it may deposit onto the electrodes. But organic molecule generally does not have that tendency that it will be deposited on electrode. But there are some electrodes like revitrified carbon or glassy carbon. They have a high porosity, so somewhat they are and readily degradable also. So after 3 or 4 reactions, generally what we find out that these electrode we cannot use after 3 or 4, 5 cycle, even though we have to sonicate, and after every reaction that there are some problem associated with that. But the product we are getting in the solution phase only.
Okay.
Yeah. General solvent generally prefer those which are oxidatively not that fragile. Means the oxidation potential should be little bit higher in the range of the 4 or 3 or 4 like this, because generally whatever the voltage or the galvanostatic condition where the constant current have been used, generally 3 to 4 ampere are good enough to do the reactions. And most of the cases, we use the acetonitrile. We start generally with the acetonitrile. It is the same process. What we do in organic synthesis, that random on the basis of some assumption we can start, but the acetonitrile is one of the prime solvent we want to use. And apart from that, but these organic solvent we are using, it requires a lot of electrolytes also, since the electron transfer has to take place. But if we can use water in that, then the electrolyte quantity may be decreased. But as in all the reaction, we cannot also use the water.
Water solubility in your substrate.
So generally, yeah, but no, not completely in water. The mixture of the organic solvent with water with the HFIP also I've used, but the thing is HFIP again is very costly. So again, we have to recycle every time the HFIP, even though we are using the 6 ml or 7 ml, that also we are recycling. So in that respect, I tried the mixing of organic solvent with HFIP, but in that respect, we were not getting the yields.
That's so.
Now I request Professor Patel, sir, to please felicitate our invited guest, Dr. Siddharth, with a token of respect. Thank you, sir. I now request Professor Mishra, sir, to introduce our next invited speaker, Professor Rajiv Sakhuja.
Yeah, in this session, I think that he will be the last speaker, I think.
Yes,
Professor
sir.
Rajiv Sakhuja is the next
Yes, sir.
speaker of this session. He is an associate professor in a very prestigious institute, BITS Pilani. And he did his MPhil and PhD from organic chemistry from University of Delhi, and followed by one of the postdoctoral from Florida. He has a lot of administrative experience, like he's a member of Central Purchase Committee and Teacher Learning Center, and he's the faculty in charge also of Institute of Functions and all. So with these things, I would like to invite Professor Sakhuja for his lecture. Yeah, Professor Sakhuja.
Yeah, thank you, Professor Mishra, for the brief introduction, and thank you to the organizing committee, especially Dr. Pratibha, who have been my classmate in masters also. So she's also doing a great research over here, especially at the college level. Just to correct one small, I'm now a professor being promoted a few days back. But
okay,
nevertheless, that's not important. That's not important. The important thing is to talk about research. So let's talk about my work. So I joined BITS Pilani in the year 2012. And yeah, it's not working. Yeah. So Pilani is situated on the borders of Haryana and Rajasthan. It's like 200 kilometers from this place. It's a very beautiful campus. I invite all of you to come to campus. The Department of Chemistry was established in the year 1964. It's one of the oldest departments. And we offer undergrad, MSc degree and PhD degrees. And we have right now around 21 faculties, 80 PhD students working in the area of organic, inorganic, physical chemistry, theoretical chemistry, and other interdisciplinary work. I started my journey, as I mentioned, in the year 2012, when I moved from Florida to this great institution. And, I must say BITS Pilani is magic, if you start living over there, you really don't feel like coming back to Delhi, though I am born and brought up in Delhi. But now I really feel like staying all my life over there in Pilani camp. It's not moving. Okay, so my research group have been working in last couple of years in the area of core organic synthesis, but of course, with the demand of working in interdisciplinary work, we are exploring the applications of the organic compounds that we are synthesizing in the area of organogelators, chemosensors, anti-cancer agents. But today's talk is primarily focused on the development of methodology that we have done over the last few years. It's very, very important for the audience that I'll share what exactly I'm working on. So CH activation is not a new term. It's been developed for the last 20 years. But the impact of the CH activation has created wonders. And it has made chemistry really, something which was unimaginable or, if I talk about, can you join two benzene rings, 20 years back, the only reaction that comes to all of our mind is, the only Ullmann reaction where an aryl halide or an aryl halide can be combined in terms of sodium. But over the years, what has happened with the invent of cross-coupling reactions or metal catalyzed cross-coupling reactions starting from 1976, and 3 people who got the Nobel Prize under the platinum catalyzed cross-coupling reactions, the chemistry has actually, moved forward towards the flourishing modern concept, apart from the conventional chemistry. Moving forward from cross-coupling, I think the CH activation concept came into limelight around 15-20 years back when, when usually we talk about cross-coupling reaction, the need for a pre-functionalized starting material. Usually have a leaving group on an aryl or a vinyl system. But what if we don't have a pre-functionalized system? What if it's difficult to pre-functionalize a starting material having an aromatic and a heteroaromatic system? So I think this concept came into picture that yes, even that CH or the unactivated CH can be activated by using appropriate metal catalyzed system. Both these strategies which are shown on the slides have their own disadvantage and advantage in terms of reduced selectivity, in terms of optimization conditions, yields, and so on. But of course, CH activation concept over the last 20 years has done very remarkable strategies produced towards synthesizing complex scaffolds, heterocyclic scaffolds. More specifically, this concept is more important and more impactful when another concept has been joined with this, and that concept I'm talking about is the impact of a directing group. Is the highlighter not working? Which one? Okay.
Over there.
This one? Okay, thank you. So the concept of directing group is basically installing temporarily or a permanent directing group on a heteroaromatic or an aromatic system, which can actually activate, a neighboring unactivated CH bond, and then helps in coordinating or affixing a functional group or an annulation process via formation of some complex transition states. That was the concept. It's not been developed by us, but it's a very well recognized, exemplified concept that has been used over the last 10-15 years. More specifically in this area, several directing groups, including functionalities like amides, ketones, carboxylic acids, and whatnot, and even heterocyclic moieties like pyridine, quinoline, have been employed where these groups have been installed on an aromatic or an heteroaromatic system. And then with the help of an appropriate metal catalyst, rhodium, platinum, ruthenium, nickel, cobalt, most of these catalysts, they are able to, coordinate and undergo CH activation at the unactivated site. And then this helps to coordinate a reagent or a functional group inducing reagent to either go functionalization or annulation to produce various scaffolds. We started our journey on these two systems 5 years back in 2018, where we wanted to explore the impact of the internal inbuilt cyclic amide presence in indazolone and thalazinones towards accompanying or accomplishing functionalization or annulation on these two systems.
Only just forward and backward, please.
Okay, so this is not even moving. No, that's fine. Slide share is not even happening. It's not moving. So it's fine. I can work without laser pointer, but what I need is a slide changer. Okay. So of course, the first question comes to us is why these two systems? Of course, these contains privileged heterocycles like indazoles and thalazines, which comprise of several natural products and synthetically developed drugs, which are oriented towards the system. And that's why we started our journeys with these two systems. At that moment, when we started the journey, very few papers were published, or very limited work was available on these two systems, and we started in 2018. And what we did is we did a couple of annulation 4+2, 4+1 annulation by reacting these scaffolds like thalazine 1,4-diones with diazocarbonyl compounds, with sulfoxonium ylides, with acrylates to obtain a series of 4+2 or 4+1 cinnoline fused thalazinones, cinnoline fused indazolones, and so on. I'm not going in details of this. I'm going to talk about some new work that we have done in the last 2-3 years. Similarly, we also applied isocyanates as the coupling partners and annulated and obtained either the functionalized version or the annulated version in which carbonyl insertion was obtained using the isocyanate with an elimination of the aniline in the strategy. We also use melamine, we also use nitro-olefins to obtain the corresponding fused 5 or 6 membered cyclic systems through all these starting materials. So this will be published till 2021. I'm not going to show all this. I'm moving to a next project in the same series where we started working on annulating or proposed that allenes can be used and can be annulate with our starting materials. Now, allenes, if we see if we talk about the reactivity patterns of allenes, they are more or less like alkenes or alkynes. The only thing is they are very difficult to prepare and very difficult to handle also. But in fact, when we started working on this, there were a few papers where allenes have been used to undergo alylation, alkenylation, allenylation, diallenylation, and annulation with a variety of heterocyclic or simple aromatic compounds. However, if we further attached electron withdrawing group like an ester, the reactivity of an allene further increases. However, this particular allenoate is capable of reacting in different formats depending upon the synthon it's generated. So taking an advantage of the reactivity patterns, we searched some literature and we found that there were a few publications by others where allenoates have been used in coupling with different heteroaromatic systems to obtain the corresponding fused compounds under different metal catalyzed conditions. Taking in leads from these compounds, we started our work on coupling allenoates with indazolones. Obviously, as an organic chemist, the first task is to optimize the reaction conditions to see what kind of products we are obtaining. And to our surprise, what we obtained is that by using different solvents, dioxane and acetic acid, 2 different versions or 2 different regioisomeric forms of the product were obtained. One having an internal double bond, the obtained fused cinnoline structure, while in the other one, the exocyclic double bond was obtained. This was very surprising to us. It took actually a lot of time for us to characterize these compounds because there was very small difference in the 1H NMR of these 2 compounds. Having optimized and characterized these compounds by detailed spectroscopic studies involved, including X-ray of model substrates, examples, we synthesized a series of compounds by making modifications on the aryl part, on indazolone parts, and of course on the allenoates part as well. Using the second condition, acetic acid, also we varied and prepared a series of compounds to obtain the fused cinnolenes containing exocyclic double bonds. To our surprise, what we observed is that when we took substituted allenoates, we only obtained the product containing the exocyclic double bonds in either of the 2 conditions. Either we use sodium acetate or we use ozone, we only obtain this one particular type of product. The products obtained were completely characterized by the X-ray studies as well. On the other hand, tri-substituted allenoates did not work in the reaction. Of course, the next task was to understand the mechanism, for which we did a couple of mechanistic investigation, including control experiments, kinetic isotope effect, and we understood the mechanism as the following, that the reaction proceeds by a CH activation by platinum, which is the main catalyst, which we found to be the best under the optimized condition. And this leads to the formation of a 5-membered cyclic pallada cyclic intermediate B, which upon coordination and migratory insertion forms a 8-membered pallada cyclic intermediate D, and it ultimately leads to reductive elimination to form this exocyclic compound, which under presence of sodium acetate leads to a more stable product, which is 3. If we don't use sodium acetate, the major product obtained is the compound O, which is the compound containing exocyclic compound. From here, we move to a second project in the similar lines, and now we picked up quinones as the annulated medium, because quinones have been ubiquitous in nature. And a number of benzoquinone, naphthoquinone derivatives have exemplified versatile biological activities. So we were interested in seeing that what will happen when our systems will be coupled with quinones. Of course, there was some literature where quinones have done annulation or spiroannulation, and sometimes alkynylation or hydroarylation with some starting materials. We started our optimization studies, and we found that ruthenium, in this case, is the best catalyst to obtain the corresponding spiroannulated product in toluene using cesium acetate as a base. Using the optimized studies, we prepare a series of compound. This is a very interesting interpretation, because the NMR interpretation of the compounds was very important. I'll tell you why. Because when we use different unsymmetrical quinones, there was a chance that we can get two different regioisomeric forms of the products. We have carefully analyzed each one of them. In some cases, we get a mixture. In other cases, like where we have a tertiary butyl case, we get only one regioisomeric form, which we have completely characterized with the help of NOE studies. So we get this. Also, the chemical manipulation of the obtained product was done by either doing a hydrogenation of the double bond with H2PDC or sodium borohydride in excess, where we found that, to our surprise, apart from reducing the two carbonyls in quinone, the double bond was also reduced. So these compounds were also completely characterized. What we also observed was something different now. So what was observed that if we have a two substitute of an ortho substituted, I'm so sorry, the marker is not working, a substitution over here, then what was observed that spirocyclized product was not obtained, and what we observed is a fused annulated product was obtained. This was very surprising. We still don't have a reason for it, but this is what we obtained. And with this condition was only valid only for ortho substituted phenyl substituents, not for other substituents. So in these cases, we obtained the fused products in appreciable decent yields. Some of the starting materials having chlorobromo ortho substitution did not work under these conditions. Of course, we started working on the investigation, mechanistic investigation. We did a few control experiments. We did deuterium labeling experiment, KI studies using intercompetitive and parallel experiments to determine whether CH bond activation breaking is involved in the rate determining step. And of course, we try to see if somehow we can monitor the formation of an intermediate through mass HRMS analysis, because we could not isolate any intermediate by the routine process. And it's a very similar mechanism that I've shown earlier. The mechanism involves the formation of a 5-membered cyclic Ruthena cyclic complex. But here there are two different courses or pathways which leads to either the formation of a spirocyclized product or an annulated product. But till date, we don't have an answer. Even when we submitted this paper, we were asked that propose a reason why is it so that ortho-functionalized products are not leading to the spirocyclized product. But sometimes people are clueless about the mechanism, and that's why we propose mechanism. Anyways, the next in the series is something that we have recently done. Idonium salts again are very, very important partners for introducing the aryl group. They're very easy partners to handle and to play with. And idonium salts have been used for arylating various aryl and heteroaryl systems in the past. We wanted to use idonium salts for arylating the ortho position, taking an advantage of the directing group behavior of the inbuilt amide group present in thalassinone. And this is where we started this project from. And we found that under platinum catalyzed conditions, the ortho-functionalization was achieved using cesium acetate as a base and xanthose as a ligand. Further, we found that with a series of conditions, with the condition in our hand, we synthesize a series of ortho-arylated products. And when we use unsymmetrical idonium salts, what we found that the substituted aryl version is preferably arylated as compared to the unsubstituted aryl version. But in one of the cases, we do get a mixture like bromo substituted idonium salt. We do get a mixture of bromo and the unsubstituted regioisomeric mixture together. Thereafter, we also found that if we increase the equivalence of the iodonium salt, then of course CN and arylated products, diarylated products was also formed. We did some mechanistic investigation in this case, competitive experiment, INPO results to eliminate the possibility of radical mechanism. And also we perform an experiment where we see that the role of sodium acetate is just for the CH activation step, or it's also been involved in the N-aerylation. Based on these experiments, we propose that it involves two different steps which happens one after the another. So formation of a 5-membered Pallada cyclic intermediate, which undergoes coordination and then further aerylation to obtain the compound product 3, and which can further undergoes a second subsequent step without the involvement of platinum to form a CN aerylation product. This is a very interesting project, and this is a very surprising result that we obtained. So we were working on indazolone, and we were trying to couple carbenes with indazolone using N-tosyl imines actually. And we found something very interesting in this entire story. And we found quinozolones, and that's what this entire story is all about, because these are very, very interesting targets. And a large number of natural products and synthetic drugs contains this nucleus. If we see the literature methods available for these systems, we have two different types of substitutions that can be possible. So here you can see we have substitutions at 2 and 3 positions. And so these different methods are obtained. These are conventional strategy, talking about taking isotoic acid and then reacting a multi-component reaction in presence of different Lewis acids and other material to obtain this compound. A very interesting report was published by Gogoi and co-workers where they took indazolone and they reacted this with alkynes. And what was happening is that there's a nitrogen-nitrogen bond breaking is happening. And I'm sorry. And there's stopping or scissoring of this triple bond, and this gets inserted between the two nitrogen bonds. So taking an inspiration from this, we started working on reacting indazolone with N-tosyl hydrozones. And then what we observed is that under platinum catalyzed condition, what is happening is that there's an insertion of the carbon containing an aryl group between the nitro-hydrogen bond, and will result in the formation of quinozolones from this in very high yields. Of course, the optimization conditions were tried, bases, the equivalence of bases were tried, and we found that equivalence of cesium carbonate is the best condition to obtain this. This looks like a typical carbene chemistry, but after carbene formation or pallada carbenoids, something else is happening. That's what we try to investigate. Of course, with the conditions in hand, we did functional modifications, substrate scope on diversification on indazolone, on the substrate, and we synthesize a large number of compounds in the series. From one aryl or one substitute indazolone, we applied the same strategy to 2 substituted indazolones, and we obtained the corresponding 2,3 di-substituted quinozolones very comfortably. We also applied the strategy towards the synthesis of a bioactive molecule, MPS 53574. This is an antagonist, and we comfortably obtain this in very high yields on a millimole gram scale. Big challenge, we had a lot of trouble while publishing this work, especially because the reviewers were not convinced about the mechanism we were proposing, because we didn't have enough proof. So we submitted to a high journal, but eventually with the limited mechanistic, it was published finally to a JOC. But what we observed is there were very beautiful observations we observed. So when we have a substitution over here, for example, when we reacted this with indole or para-hydroxy phenyl substituted substrates, we obtained that the quinozolones were not formed. We actually obtained the corresponding N-substituted alkyl systems. This was a very surprising result showing that there is some involvement of an hydroxy or the NH acidic protons in this reaction, which is hindering it to obtain the quinozolones by the usual route. We also methylated, hydroxy to the corresponding methyl to just see whether now there can be a rearrangement from this N-alkylated product to the final product, but this never happened. we tried to monitor some reaction product intermediate formation in the HRMS. Okay, we did try to monitor the intermediate formation in HRMS, and we found one of the proposed structures in HRMS, based on which we proposed this beautiful mechanism where the first 3 steps are very simple, well-known logic, formation of carbenoid formation, pallada carbonate formation, and thereafter there's a sequential NN bond formation and insertion of the carbene inside the bond formation to form either product 3 or 5. In conclusion, the last couple of years, using these 2 starting material, we actually explored this widely towards annulation and functionalization under ruthenium, rhodium, and palladium catalyzed conditions in a variety of manner. And these are all biologically active molecules. Some of them are under way. The problem with the organic chemist is that, activity determination takes time, and we don't have time because others are working in the same area, and we have to publish ASAP. So that's what is the problem. Very recently, last year, we started work on expansion of the CH activation on amino acids and bile acids. So these are 2, I'm not going in details of the papers. These are the 2 works we published last year and this year. Working on amino acids is very challenging, because the expectations from the reviews are too much. The reason is that if you publish a paper in heterocyclic area, you can prepare 15, 30, 35 examples very comfortably, though it requires a lot of time. But when you propose area of amino acids, the expectations are same, but preparing dipeptides, tripeptides, and doing the same chemistry over there is very challenging. But anyways, we have done the functionalization on tyrosine. Again, the concept is CH activation, the first one. It's a very beautiful chemistry, and we have explored this for late stage peptide functionalization on tyrosine containing peptides. Very recently, a few days back, we published this where we have actually activated the beta position of bile acids by installing this auxiliary, quinoline auxiliary at the carbonyl C24 carbon, and achieved the aerylation or heterylation at the CSP3H, which is actually difficult. So these are the 2 things we have done. I'm almost done. It's very, very important to acknowledge my. I have a group right now. 5 students are working. 5 have already graduated. But the work I presented is being done by Karishma and Sushma. Of course, we cannot proceed forward unless we have funding agency. So I'm very thankful to my host institution, BITS Pilani, DST SERB, CSIR, UGC, DST, for the infrastructure and funding possibility. Thank you for your kind patience. So sorry, I've gone through some of these slides. I will be able to answer questions.
Activation. Last you saw that you have just coupling of that peptide.
Thank you, Professor Rajiv Sukuja. Now session is open for a couple of questions.
You have just coupled that your peptide. Peptide very just a soft molecule, and maybe structure is changed. Maybe we are working proteins, peptides.
Right. So
if someone coupling with that type of conjugates and peptides in the molecules, it maybe structure may be destroyed.
No, sir. What is happening is we try to prove that. So what we work is basically try to do the same. So first we do is we try to optimize condition on a simple tyrosine system.
Tyrosine.
Yeah. So once that is established, we prepare a series. I have not shown this word, but we prepare a series of compounds. Then we apply the same condition on dipeptides, tripeptides, and tetrapeptides in solution phase by the optimized condition and see whether the reactions are working or not. Finally, we also prepare the corresponding DL version of the same starting material to see whether there is a racemization happening during the process. That is your concern. That is your concern. I totally understand. So we have established that by taking a model example or model substrate having DL starting material, and we have done the HPLC to prove that there is no or almost no racemization observed during this process.
Nice.
Although, this is a myth that usually when reactions in amino acid happens at high temperature, there are chances of racemization is very much high. We were applying very harsh conditions here. It's 80 degree. We are recently working on another project where we're using 100 degree. That's under revision. But, the reviewer asked again the same thing. And we have done a DL preparation starting material. And we found that, the reaction is almost avoiding any racemization. There's no racemization happening. Yeah, but when we move to tetrapeptide, Yes, there is something happening. Isomerization is happening. We are observing that in NMR. Absolutely. We are observing that. That's even visible in NMR also. That's even visible in NMR. Yeah. Okay, thank you so much. I invite you all to BITS Pilani. You can all welcome. You are all welcome to come to BITS Pilani. Thank you so much. Pleasure meeting.
Thank you, sir. Now I request Professor Patel, sir, to please felicitate Professor Sakuja with the token of respect. With this, we come to the conclusion of a very interesting, stimulating lectures of session 4. I now request Professor Mishra, sir, to please conclude the session.
Thank you, Dr. Nandi. Really, this is a very hard work for me to conclude being a theoretical physicist. I'm theoretical condensed matter physicist, actually. I play with equations and all, and never I play with organic molecules. And so I generally, if you go through my publications and all, you will find only mathematical equations and derivations, and those mathematical, and then development of software for material design. Okay, so in this very good informative session, we have 4 speakers. And one thing very important I would like to share with you people. First 2 speakers, Professor Ram Singh and Professor Jha, both were from Ranchi. Both started their career, schooling and all from Ranchi. And next 2 speakers, both were from Rajasthan. That's a very good thing. And all 4 were very renowned organic chemists. If you find that Professor Ram Singh lecture, so he actually, what he did actually the detailed analysis of Alzheimer's disease and its, you can say that its status at international level and India level, how it is affecting. And then he followed by explains synthesis of some molecules, organic molecules applicable for the treatment of Alzheimer's, and for which he filed a patent also. And then I'm coming to the Professor Amit Jha. He gave the synthesis of large number of organic molecules using green techniques, and whatever the side product was coming during the chemical reaction, that side product also he converted into useful drug molecules. And basically his drug molecules were applicable for cancer treatment and bacterial infection treatment of today's lecture. And then I go to the Dr. Siddharth Sharma. And if you see the Professor Siddharth Sharma work, he is the electro-organic synthesis using a control current value. And because I feel that the current value can degrade the product also. And most of the solution was product was in solution phase. And this anodic and cathodic oxidation reduction reaction, he using electrochemical technique and synthesize very innovative new molecules, organic molecules also applicable for the various chemical applications. Then the last speaker of this session, Professor Rajiv gave a lecture on palladium, ruthenium, and rhodium catalyzed organic reactions. And his organic molecules were also applicable for various chemical application. And yes, no doubt about the drug purpose. So from my side, this is the conclusion of these 4 lectures. And now I think Dr. Nandi will give the vote of thanks. So now.
Thank you, sir. My heartfelt gratitude to Professor Mishra, sir, and Professor Patel, sir, for chairing the session. Now I request Dr. Revti Menon of Political Science Department, Deshbandhu College, to please felicitate Professor Patel, sir, with a token of respect.
And Mishra, this is drawback of that online. You are there, but I am over here.
That's good, sir. Sometime I will
Yeah,
come
yeah,
over
yeah.
there
I miss
because
you actually. I really miss you over
Yeah,
here.
yeah.
Actually.
I will meet
One-to-one.
you, sir.
Yeah, thank you.
Actually, I have very good relation with the University of Delhi. My wife is in Karodimal College.
Oh, nice, nice, sir, nice. Okay.
Mm. And I think some of faces are known to me.
And our team who organized the West Bengal Forum with conference and all of you.
Thank you. Respected Chairperson, invited guests, delegates, and my dear students, as we come to the end of session 4 of ICHE 2023 organized by Deshbandhu College, I, on behalf of organizers, take this opportunity to thank our distinguished chairpersons for gracing this occasion with their intellect presence. I also express my sincere gratitude to the invited guests and speakers for intellectually enriching us and updating us with the cutting-edge latest information and technology. I also take this opportunity to thank all the participants and audience for interactive and engrossing attention. I also thank non-teaching staff and students for working behind the scenes. Last but not the least, I thank Dr. Pratibha ma'am for giving me the opportunity to be the part of this international conference. I, on behalf of organizers, invite you all, guests and delegates, for a high tea in conference room and request you to join back for the session 5 at 11:45 a.m. It is a tea break for 15 minutes. Thank you. Just a second. Dear delegates, just a second. We also have an announcement. I request my IT team to felicitate Professor Raj Kumar Mishra sir with the token of respect. Please put your hands together.
Thank you. Thank you very much.
Thank you, sir.
Yeah, thank you. Okay, now, may I leave now?
Yes, sir. With your permission, we can
Okay.
close the session, sir.
Yes, please,
Thank you,
please,
sir.
please.
Thank you, sir.
Okay. Thank you to all of you.
Thank you, sir. Thank you, sir.